Distinguished participants and dear colleagues, in my role as a president of the International Astronautical Federation, it's my great pleasure to welcome you today to this exciting IAF GNF Space Conversation series. Responding to the success of this really brand new initiative, the Federation is committed to continue offering a free of charge virtual program to the entire IAF community worldwide via this IAF GNF Space Conversation series. And the IAF will therefore continue to provide the space community with a unique platform to connect, share ideas, and grow together in the line with its motto of connecting all space people. And I think this is in particular important in those times where we are still partly banned in home office and we really need to stay connected. So today's session is organized by the Berkeley SETI Research Center, which is an IAF member since 2009. And the topic will be Breakthrough Listen and International SETI Collaboration. So a really exciting topic. So Breakthrough Listen is a science project based at the University of California, Berkeley, and representing the most powerful, comprehensive, and intensive search for extraterrestrial intelligence, which was ever undertaken. And using sophisticated radio and optical instruments, astronomers, data scientists, and computer engineers hunt for so-called technosignatures, electromagnetic transmissions of artificial origin. So in today's panel discussion, research collaborators across the globe will highlight the international and global efforts that have been made to detect these signatures. So, but before we dive into this really extremely exciting project, it's my great pleasure to give the word to the IAF Vice President for Global Networking for the Global Networking Forum, Andreas Lindenthal. Thank you, Andreas, and thank you all. Enjoy the session.
Thank you very much, Pascal, and welcome to everybody. As a Vice President of the IAF Global Networking Forum, I would like to welcome you to this very exciting session. I was imagining and expecting, Pascal, with your scientific background, that you would probably highlight all the topics already of this extremely exciting session we have today. Therefore, I want to make it short. It will be extremely exciting because it's something which is affecting mankind's imagination and vision. And therefore, I'm very pleased to now give the word to the moderator of this session, Dr. Claire Isabel Webb, PhD candidate and research associate at the MIT. Thank you very much.
Thank you, Andreas, and thank you, Pascal, for that lovely introduction. Maybe since we submitted this panel, I am no longer a candidate, but in fact, a PhD. So thank you so much for hosting us as a representative of Breakthrough Listen, as a research associate there. I'm super honored that you have facilitated the session, and thank you to all the IAF members who have worked behind the scenes to facilitate the Zoom, and thank you very much for hosting us. So I am going to now share my screen. We're going to do a Google Slides presentation. I'm going to introduce the panelists and kind of the goal for the session. So please maybe let me know if this is working. Yes? Great. Okay, so IAF Space Conversations, Breakthrough Listen, and International SETI Collaborations. So this panel kind of grew out of the idea that technosignatures are gaining more and more interest in kind of the international science community. So kind of with the advent of all of the detections of extrasolar planets, we in the SETI community are very hopeful that maybe with this new knowledge of kind of the proliferation of potential life in the universe, maybe one of those extrasolar planets could include a technology using species that will have sent electromagnetic signals in the form of technosignatures that we around the world are working with international collaborators to detect. So the goal for this panel is to highlight how Breakthrough Listen is working with facilities and collaborations all around the world in this hunt for technosignatures. So the panel of scientists, we're going to discuss the history of modern SETI, update the astronomy community on the state and the stakes of the search for technology beyond Earth. So just a quick background. So the panelists are going to dive more into this, but we're midway through a 10-year duration of the Breakthrough Listen project, and the Breakthrough Listen collaboration has gathered petabytes of observational data from instruments around the world, from the Parkes telescope in Australia to the VERITAS array in Arizona. And meanwhile, the 500-meter aperture spherical telescope, also known as FAST, in China is fueling new hopes to detect such a technosignature. So Breakthrough Listen and international scientists are going to give an overview of the project, the instruments used, the data analysis techniques, the results of Breakthrough's collaboration with MIT astronomers on NASA's Transiting Exoplanet Survey Satellite, also known as TESS, plans for FAST, and the future directions of SETI research. So the goal for this panel, right, is to kind of give you kind of a taste of what we do at Breakthrough Listen, how we collaborate with international partners, but we've reserved the majority of the session for for the panelists to answer your questions. So the majority of it is going to be a Q&A. And I will tell you how to get to that. So if you go to Slido, sli.do.com, and you search for the hashtag IAF-GNF series, you can submit questions, and the IAF is going to kind of feed me those questions. And then at the end of the panelist presentation, I'm going to moderate the discussion. So you can ask a general question, you can ask individual panelists if you have questions for them. So thank you so much for being here. So here's kind of the agenda. So Andrew Simeon is going to speak first. He is the director of the Breakthrough SETI Research Center. He's the principal investigator at Breakthrough Listen. He's the Bernard M. Oliver Chair for SETI Research at the SETI Institute in Mountain View, California. Jill Tarter's talk is entitled On Becoming an Earthling, the Value of SETI. She's the Chair Emeritus for SETI Research and the former Bernard M. Oliver Chair for SETI Research at the SETI Institute. Steve Croft of Breakthrough Listen, who is also an adjunct senior astronomer at the SETI Institute, is going to kind of give a project overview of Breakthrough Listen. Howard Isaacson, who's the research scientist at the Berkeley SETI Research Center, is going to talk about the TESS collaboration. And Dee Li is the chief scientist of the 500-meter aperture spherical radio telescope FAST, also of the Chinese Academy of Sciences, and he's going to talk about SETI research at FAST. And then the rest of the session is going to be dedicated to a Q&A. So Andrew, I will give you the mic, so to say.
Yeah, may I just interrupt you very short? You go, because your slides were not on full screen. Now everything is wonderful.
Okay, yeah, sorry. Is this good?
Looks great.
Okay.
Thank you very much, Claire, for that wonderful introduction, and thank you very much for your initiative in organizing our participation in the GNF. I'd also like to thank Pascal and Andreas for the wonderful introduction to the series and to the Berkeley SETI Research Center. As Pascal mentioned, we, after many years of participation in the International Astronautical Congress, we've now become members of the IAF, and it's really been a fantastic opportunity for the Berkeley SETI Research Center to have more participation in the international space community and exposure. And we're very, very happy to partner with the IAF and participate in this series today. Claire very, very briefly mentioned that astronomers have now learned that exoplanet systems are incredibly common. Although we now almost take that for granted, nearly every day hearing about new exoplanet systems, planets orbiting other stars being discovered. It's interesting that's really been a very recent discovery. It was only in the first decade of this century that we we truly confirmed that exoplanets are as common as they are, and that really quantum leap in our understanding of our place in the universe has fueled a tremendous amount of interest in the search for life, including the question of whether or not we are alone as intelligent life in the universe. And that was really dramatically represented with the announcement of the breakthrough initiatives, a series of scientific investigations all focused on the question of whether or not we're alone as intelligent life, as any form of life in the galaxy or indeed elsewhere in the universe. The breakthrough initiatives are principally sponsored by Yuri Milner and his partner Julia, an internet investor based in Silicon Valley. The initiatives were announced in July of 2015 at the Royal Society in London. And as Claire mentioned, just in July of last year, we marked the five-year point. At the announcement, Yuri was joined by the late Stephen Hawking, Martin Rees, Astronomer Royal in the United Kingdom, Frank Drake, one of the grandfathers, if not the grandfather of the search for extraterrestrial intelligence, of the same name as the Drake equation, and also Anne Druyan, Carl Sagan's partner in his life and also in his work. Next slide, please. Thank you. As of this moment, there are 4 breakthrough initiatives that have been announced, and I'll start there in the top left with Breakthrough Starshot. Breakthrough Starshot is an effort to try to figure out how we might be able to design a spacecraft that could be propelled at a fair fraction of the speed of light, perhaps even a few tenths of the speed of light to the nearest stars to the Earth, especially the Alpha Centauri system, using directed energy propulsion. So propelling the spacecraft by using very high power laser transmitters on the ground or perhaps in space to propel a small, maybe gram scale spacecraft towards the nearest stars and get it there and return information in a human lifetime. In the top right, Breakthrough Watch. This is an effort to image nearby extrasolar planets around the nearest stars. A couple of years ago, we have a large amount of instrumentation that was installed at the VLT telescopes and some very exciting results that hint at potential new planets in the Alpha Centauri system that were just announced a couple of weeks ago. In the bottom left, the Breakthrough Discuss conference series. Since 2016, the Breakthrough Initiatives have hosted a conference series in the Bay Area of California, first at Stanford University and most recently at the University of California at Berkeley, that brings together the entire international astrobiology community writ large, including astronomers and planetary scientists and engineers, everyone with an interest in understanding the prevalence of life in the universe and how we might be able to learn more about it, to come together to address timely topics in astrobiology. And this is really a phenomenal couple of days to get together with really the very top minds in the world looking at this topic to investigate new ideas. And if anyone in the audience of this meeting is interested in attending that, please do reach out to us. This year, of course, in April, it will be a virtual meeting, but we hope that next year we will return to an in-person gathering in the Bay Area. Finally, Breakthrough Listen. This is the initiative that we're principally here to talk about today. This is a search for extraterrestrial intelligence. So relative to the other initiatives, we're attempting to answer a very specific question about life in the universe. And that is, does intelligence commonly evolve? And as we've already heard from Claire and from Pascal, we do that by looking for technosignatures for technology. If intelligent life exists elsewhere in the universe and they have developed technology in some way similar to what we've developed here on this planet, we could potentially detect those technologies via remote sensing and thereby infer the presence of intelligent life. The next slide, please, Claire. So one of the main ways that we look for technologies is by looking for electromagnetic emission that has spectral or temporal properties that are consistent with the kinds of emission that's produced by technology here on this planet, and inconsistent with the natural forms of radiation that we see from natural sources. So technology has a special property relative to natural sources of electromagnetic radiation, in that technology can compress radiation into spectral or temporal regions that are not commonly produced by natural sources. And these include things like radio signals from cell phone transmitters or from radars, to laser signals from very powerful laser systems that are used for communication, Earth to space communication, or perhaps in the future for directed energy propulsion. So to search for these emissions, we want to use telescopes, of course, all across the globe, which give us access to the entire celestial sphere, and also all across the electromagnetic spectrum. And here on this slide, you see a sampling of the many telescopes that we have partnered with in Breakthrough Listen to make sure that we can cover as much of the electromagnetic spectrum as possible, as many different modalities of signals, radio, optical, narrow band, pulsed signals, and also cover as much of the electromagnetic spectrum as possible. Next slide, please, Claire. As important as the telescopes that we're using, and this is, I think, a great segue to what Dr. Croft will talk about later in the presentation. As important as the telescopes is the technology. In fact, it's really silicon that allows us to dramatically expand the amount of the electromagnetic spectrum that we can search. There's a unique feature of the radio search for technosignatures, or radio SETI, that really directly connects the speed of microprocessors with the amount of the electromagnetic spectrum we can search. As microprocessors have moved from megahertz speeds to gigahertz speeds, and now multi-core processors with many cores operating into gigahertz, the amount of the spectrum that we can search for technosignatures has gone from megahertz to gigahertz to now many telescopes observing a gigahertz or more of bandwidth. Also, the same kinds of software technologies that are being developed for data mining in internet commerce have great applicability to the search for technosignatures. And in something of a nod to our sponsor of Breakthrough Listen and the announcement of the initiatives, we are doing everything that we can to bring a Silicon Valley approach to the search for advanced life. Which means that we try to move very quickly. We try to use the very best technology for the job, and make as much progress as we can as quickly as we can. And so with that, I'll hand it back to Claire.
Thank you, Andrew. Okay, so next we have Jill Tarter, and I am going to now share PowerPoint. Yes?
Not yet.
Not yet? Okay.
Okay.
Yes.
Okay.
You.
So thanks, Claire. Andrew has made a nice overview of the current attempts at trying to use technologies and telescopes around the world to do a search for technosignatures. And I'd like to spend the time talking about why it makes a lot of sense to put effort and time into these searches, even if it is decades or centuries, perhaps even millennia before we succeed. I think there's value in SETI that is unique to this sort of scientific in exploration. So can I have the next slide, Claire? So in the 400 years plus since Galileo's telescope began this kind of astronomical exploration of the cosmos, we have learned one thing that is profound, which is that it actually takes a cosmos to make a human, right? You and I, all of us, everything around us is literally made of stardust, that fine old Carl Sagan quote. So we fit into the cosmos. We are a part of that ethos. And we'd really like to understand whether there's anyone else, anything else out there with whom we could exchange information. And that requires us really to use a cosmic perspective on all of these questions that we ask. So Claire, the next slide. So for SETI, or the search for technosignatures, to succeed, two technological civilizations need to be close enough together for us to be able to detect one another, or for us to detect them. And the only way that that can happen is if, on average, technological civilizations live for a very long time. And that's long in cosmic terms, not human terms. So we are a very young technology, we Earthlings, in a very old galaxy. And we have no idea whether it is possible to become an old technology. But if SETI were ever to succeed, Claire, can I have the next slide? Then we instantly understand that it is possible for us here on this planet to have a long future, because success in SETI requires longevity. And thus, as Philip Morrison, one of the pioneers of this exploratory science, said, SETI is the archaeology of the future. It's archaeology because of the tyranny of light speed. Any signal that we receive that has information content will have taken a long time to get here because of the vast distances between the stars. And so the information content will be telling us about their past. But the fact that we do succeed will tell us that we can have a long future, because we could not have had success unless, statistically, technologies everywhere are long-lived. So next slide, Claire. So the reason that I enjoy talking about SETI and the search for technosignatures to groups everywhere is because I think that the discussion and the consideration of someone else's technology out there, in fact, holds up a mirror to all of us on Earth. And in that mirror, no matter how different we might appear superficially, we humans are all the same when compared to something else, somewhere else, that evolved independently of this planet. And I think that this opportunity to help people to think beyond their normal frame of reference, to consider the fact that compared to them, all of us on this planet are exactly the same. It trivializes the differences among humans. And I think that's really important for today's situation, where there are many, many challenges that face us on this small planet that will not be solved nationally. These challenges don't respect national borders. They require global cooperation in order to succeed. And I think that anything that we can do, primarily in our case, talking about the evolution of life here on Earth and the question of life beyond Earth, anything that we can do to trivialize the differences among humans is beneficial and helps us to adopt a bigger perspective of who we are, where we are, when we are. And so I think that I totally agree, Claire, the next slide, please, with Caleb Scharf, the chairman of the astrobiology department at Columbia University. And Caleb is fond of saying that on a finite world, that's us, right? A cosmic perspective isn't a luxury, it's actually a necessity. And so I would urge anyone listening to this talk, the series of talks, when we're done, go to your electronic devices where you store a profile of who you are. And I'd like the first thing that you say about yourself is that you're an Earthling. And then just think about it and try to act like one. Thanks.
Thanks, Jill. What a lovely thought for these times. Okay, so next, Steve Croft, Dr. Steve Croft of Breakthrough Listen, and I'm going to go back to the Chrome presentation. Okay, the Google presentation. Yes?
Great, thanks, Claire. So I am the project scientist for Breakthrough Listen on the Green Bank Telescope, and what you're seeing in the left picture here is our chief engineer, Dave McMahon, standing looking up at the Green Bank Telescope. It's the world's largest steerable single dish radio telescope, 100 meters in diameter, and Breakthrough Listen has 20% of the observing time on the GBT to look for radio technosignatures. And the way that we do that, as Andrew already alluded to, is using commodity off-the-shelf hardware. You can see the instrumentation on the right here. This is actually just half of the cluster that we have out at Green Bank, which acts both as our observing instrument that actually gathers the data and streams it to disk, and also as part of our analysis cluster that searches for the signals. We're writing hundreds of terabytes per day of raw data to these disks that are stored in these machines. There's GPUs that are in there, graphics processing units that are used to actually do some of the processing on these. And then the actual search that we have to do is really, we've likened it to looking for a needle in a haystack. And there's a huge haystack of signals out there. Andrew already mentioned about the signals that human technology generates. And so our task really is to find, are there any needles in this haystack, really without necessarily knowing very much about what those needles might look like. And how we might go about finding them. So I just wanted to sort of tell you briefly about one of the techniques that we're using. And Claire, next slide, thank you. So hopefully this video is going to work, and this is how we actually observe. You can see here, there's a little reticle in the middle that's moving on and off the star Vega. So we're looking at a star for 5 minutes with the Green Bank telescope, and then we're moving to a nearby position for 5 minutes. And you can see in a second, we're going to pan across the sky to a different star, to Procyon, again, moving on and off the star. And you can see the positions of satellites are plotted here in this animation that I generated using this free software, Stellarium, great planetarium software. And you can see that if we're able to just isolate the position of a signal on the sky as coming from that star, that we can rule out it coming from the satellites or from other earthbound interference, from other things that are not moving with the sky as the star is tracking across the sky. And so this is a spatial filter that is one of the methods that we use to try and sort of get through this haystack, to try and really throw away a lot of the hay, and to hope that what remains is more likely to contain these needles, these technosignatures that we're looking for. What we get out when we run this analysis is a spectrogram. So again, as Andrew mentioned, we're tuning to gigahertz wide bands of the spectrum. We're essentially sort of, you could think of it as listening to 1 billion radio channels at a time. And yeah, Claire, if you can go to the next slide, you can see what this looks like. So here are 6 spectrograms. So this corresponds to these on and off observations. And if you click on that slide, hopefully the little animation will work here. So on the star, off the star, on, off, on, and off the star. So this was the corresponding again to this reticle that was moving on the star. And you see these scans again corresponding to 5 minutes in time on the vertical axis, and a whole bunch of frequency channels on the horizontal axis. And your job essentially as a SETI researcher is to find features in these images, and then potentially, you know, as I've sort of shown in this cartoon here. Oh, sorry, could we just go back one?
Yeah, sorry, I don't know why.
Thanks. To find features in these images that are only present when we're actually pointed at the star in question. And so I've sort of put these in as a cartoon feature here. I guess it's just going to shift forward to the next slide, but hopefully you get the point. And if you've seen these sort of things, you know, with self-driving cars, essentially computer vision systems that can draw boxes around things and then look for anomalies, this again ties back into what Andrew was saying about the Silicon Valley approach, about how we really want to sort of be able to extract signals from images to look for anomalies. And that's a real focus for the team right now. So now if we actually can go to the next slide, hopefully there's not going to be animation problems here. Here's just a few things that we're trying. I really just wanted to sort of give you a flavor. I'm not going to dive into any of this, but we're using convolutional neural networks, which essentially is what Google uses to sort of give you cat pictures if you're searching for cats in Google image search. We're trying, you see on the bottom right here, sort of a similar picture to what I just showed you in the last panel. And these are some folks in industry at a company called DeepSig that have trained an algorithm to recognize signals from cell phones and distinguish them from signals from Wi-Fi and distinguish those from Bluetooth, and essentially training, again, a machine learning classifier that we're hoping that we can then scale up to deploy on the data that we're taking with Breakthrough Listen from Greenbank. We have a great team of undergrads, including some computer science undergrads that are really sort of pushing our analysis into the cloud using Google Cloud and the technologies that sort of come along with that. And as part of that as well, we're also going to launch a competition with Kaggle. This is a machine learning competition and data science platform that's actually now owned by Google, but we've been working with them to hide some artificial needles in the haystack of data. And then we're going to challenge the world. We're going to challenge, hopefully, including some people on this call who might have some smart ideas about how to find these features in images. We're going to challenge you to extract these signals from this noisy background to sort of get better at finding needles in haystacks. And perhaps you'll actually even find a real technosignature. Maybe we're just waiting for that technique that will find the signal that we've been looking for that might be on disk somewhere, either in our public data archive at Berkeley or on the disks at Greenbank. And so we'd really like to sort of share this journey, this sort of adventure, this discovery with the world. And we hope that you'll get involved. In particular, look out for this announcement from the Kaggle competition that should be coming pretty soon. Thanks.
Thank you, Steve. How exciting would it be for a listener to this webinar to find a technosignature? That's so exciting. Okay, next we have Howard Isaacson, and he's going to talk about the TESS collaboration.
Thanks, Claire. My name is Howard Isaacson, coordinator for the TESS collaboration at Breakthrough Listen. And so far we've heard from Andrew and Steve the sort of wide variety of telescopes that are available and data products that are available from those telescopes, primarily focusing on the radio search for technosignatures within Breakthrough Listen. So I'm going to talk a little bit about the optical SETI searches that we have going on, specifically the one that involves NASA's TESS satellite. TESS is in orbit around the Earth in a synchronous lunar orbit, observing a small portion of the sky well, a large portion of the sky for about 30 days each. You can see the depiction up in the upper left here that shows that as the telescope twirls around the ecliptic sky, there's one part of the sky that has near continuous coverage, which is coordinated with the James Webb Space Telescope continuous viewing zone, and covers nearly 80% of the sky. And the data product that's produced is different than what was described earlier, when in the sense that our typical radio searches look at a single star or a single point in the sky per observation. The TESS telescope looks at a very wide angle, making brightness measurements of millions of stars at the same time. The collaboration that we have working at this point is primarily focused around the TESS science team at Massachusetts Institute of Technology. And we also have collaborators from across the country: NASA Ames Research Center, University of Washington, and Penn State University, just to name a few. Next slide, please, Claire. So what does TESS measure? Well, TESS measures brightnesses of stars every few minutes across huge swaths of the sky in order to produce what we call light curves, which are depicted up here in the upper right-hand side. And over time, stars have all kinds of variations in their brightness due to star spots, due to flares, different kinds of stellar activity and pulsations. And what we're looking for are really unique features in light curves that are very difficult to explain astrophysically. Due to the really huge numbers of light curves, really we have now tens of millions of these time series brightness measurements for stars. And we can use modern techniques similar to those that are used in data science and also in our search in the radio to identify different classes of stars, to put these light curves into bins of known activity, of known sources. Of course, binary stars and supernova and these types of things are the most dramatic. But we're looking for things that have no explanation from a science or astrophysics perspective. We're looking for really the most unique things, and in order to find those, you need to just do these really broad surveys with many millions of stars to find the most interesting, those that might be a Dyson swarm, that might be evidence of something that some kind of technology. So this is really exciting. The TESS mission is ongoing. It's observed over 80% of the sky and is now doing a repeat of the southern ecliptic zone. We have 80% of the sky already, with just huge amounts of data coming in all the time. And of course, this is but a segue into the LSST telescope, which is coming online in the next few years, which will offer an even a ground-based survey of the night sky on a sort of once every few weeks. A real nice complement to something like the TESS survey, which does these millions of stars at a time measurements. And yeah, it's a really exciting collaboration, growing all the time, really trying to complement our SETI radio searches with a very nice optical component as well.
Thank you, Howard. It was good to get updated on all of Breakthrough's new activities. Okay, so now we're going to go to Dr. Dee Lee, and he's going to talk about the FAST telescope. Okay.
Oh, thank you, Claire. Can I be heard?
Yes.
Okay, great. So yeah, this is, as Claire has introduced, this is the so-called 500-meter aperture spherical radio telescope. It's largely motivated by the Arecibo telescope. It's a very light structure. So what you're looking at is that you can see that spiral light. That's actually a truck that has been driven underneath the dish and going to the center of the depression. So more than 50% of the area you are seeing is actually empty because they are made of tiny holes that are much smaller than the wavelengths. So they are, so the whole dish can still function as a perfect or efficient reflector. So it's that physical diameter is 500 meter, and it translates into a surface area of about 30 football field. And if we filled up this whole walk of antenna with, say, fried rice, everyone in the world will get at least one bowl, and depends on size of bowl, maybe even two, so you can get a second serving. So at the moment, it's by far the most sensitive single antenna in this band. So next slide, please. So it took about 20 years of proposal and about 6 years of construction, and we only transited into normal operation from early of last year. So within the last year, there have been a few tens of scientific papers published, and I think one of the major developments is that we have demonstrated this new observing mode that we can take normal sort of astronomical science data, such as imaging the neutral hydrogen in the Milky Way and galaxies, search for so-called pulsars, which is fast spinning neutron stars, as well as doing search for extraterrestrial intelligence. And based on this commensal observing mode, we are now doing the so-called the commensal radio astronomy fast survey, or AKA CRAFT. So what you can see in that lightning-like signal is actually a real pulse we detected. That's toward this so-called fast radio burst source. It's a mysterious cosmic radio flash. And we don't know the origin, but in 1/1000th of a second, it produces energy given out by the sun, radiated in about a year. And some of our colleagues has hypothesized that it's also one kind of extraterrestrial intelligence, although it's in the minority. But while we are scanning the sky for these astronomical sources, we can also record signals that are made of technosignatures. So next slide, please. So this is a little paper that in collaboration with Dr. Andrew Simmons and our other breakthrough listen colleagues. It is discussed this simple concept that how we can quantify the result from FAST. So there's this particular plot just showing that we do have a long history of pondering upon this ultimate question: are we alone in the universe? And particularly, one of the Russian colleague, Dr. Kardashev, has tried to categorize the civilizations in terms of technical advance, so level of advancement. So the level 1 would be a civilization that can utilize all the solar energy that radiated on a planet. And according to the late Dr. Sagan, that current human being is somewhere between 0.7 and 1. And if a civilization can utilize all the energy produced by the whole star, so that's called level 2. And if a civilization can utilize all such energy produced by all the stars in one galaxy, so that's level 3. So by just a very rough estimate, the sensitivity that made feasible by the large collecting area of FAST make us sensitive enough to detect so any human-like transmitter on the nearby planets, if there are such sort of nearby neighboring intelligence that does exist. And if we train our telescope to our nearest neighboring galaxy, the Andromeda galaxy, then we are sensitive enough to up to type 2 civilization. So I think if we do this systematically at the end of our survey, even if we don't detect anything, we certainly cannot rule out the existence of such advanced technologies, but we can make a meaningful statement, and that will be sort of our small contribution to the overall drive to help to answer this ultimate question that are we alone in the galaxy? So, thank you.
Thank you so much. I feel like it was a lovely, we got all the flavors of SETI. So thank you so much to all of our panelists. And I should mention that Dr. Lee, it's almost 1 in the morning for him. So thank you so much for being here. So I'm going to start kind of asking some questions which are rolling in and have been upvoted on Slido. So Jill, I'm going to ask you this question, and I think that Dr. Lee, your kind of discussion of the Kardashev scale is a great entree into the most upvoted question. And Jill, because you kind of talked about longevity, I'm going to ask you from the audience, what are the contingency plans if the intelligent life we encounter is not benevolent in its intentions?
Claire, thank you. First of all, that's a very difficult question to answer, because how do you know what their intentions are? There's a long path between the detection of evidence of someone else's technology and decoding and understanding any information content that might be prevalent in the transmission. So I'm kind of in the Steven Pinker school on this. Any technology that could get here and therefore pose a physical threat to us is clearly older and more advanced than the technology that we have. And when you think about the evolution of a technological civilization, it's hard for me to understand how such a civilization could get to be old and sustainable without outgrowing the aggressive tendencies that we still possess and that helped us to become intelligent. So if they're old and stable and an advanced technology, I think that we don't necessarily have something to worry about. It's when cultural evolution takes over from biological evolution and leads to normative behaviors and rules of law and behavior. It's a guess, but as Steven Pinker has spent 900 pages telling us, we are kinder and gentler than we have ever been over the evolution of the human species. And if that arc continues, I think that an advanced technology is going to be curious rather than aggressive. My guess, who knows?
Thanks, Jill. Okay, so this is from Matt Kaplan from the Planetary Society. And Andrew, I'm going to give you this question because you talked about kind of the Breakthrough Listen project and the breakthrough initiatives. How do you respond to those who say that after decades of searching, it may be time to give up? And then he also says, don't worry about me, I'll always support the search.
Well, thank you very much, Claire, and thank you, Matt, for the question. I have two answers, one, I guess, philosophical and one technical, and I'll start with the philosophical one. I think from my perspective, and probably from the perspective of certainly the panel here and many of the people in the audience, the question of whether or not we're alone as intelligent life in the universe is the most profound question that we could possibly ask as scientists or as human beings. And as long as we have the capacity to do an experiment, to learn more about the possibilities for intelligent life in the universe and to possibly detect it, and even communicate with it, we should do that. I think that's a defining part of humanity. On the technical side, and there are many ways that sort of one can quantify the amount of space that has been searched, and there's been some fantastic work recently from the Penn State group about this, looking quantitatively at how much of the so-called parameter space has been searched. But here's a sort of one way to describe it. 50 or 60 years ago, there was a particular part of the radio spectrum called the terrestrial microwave window that was identified as really the very best place to conduct radio searches for technosignatures. And first Frank Drake, and then for many decades, Jill Tarter and her team at the SETI Institute have been systematically exploring this part of the radio spectrum, and we continue to do so with Breakthrough Listen, with all of the new telescopes and new digital backends that we have available to us. And yet in those many decades, the terrestrial microwave window is from about 1 gigahertz to about 10 gigahertz. In those many decades, we have only looked at maybe a few thousand stars, the nearest stars to the Earth, from about 1 to 3 gigahertz. And there are hundreds of billions of stars just in our own galaxy, and a factor of 3 or 4 more of the radio spectrum left to search. So this is just one way of saying something that's easy to say in many ways, which is we really have not looked anywhere near as hard as we could, just with the telescopes and the techniques that we have available to us today. There's just a tremendous amount of space that we have not yet explored.
Thanks, Andrew. Okay, so I'm going to ask Howard this question, and maybe you can talk about kind of the TESS collaboration and kind of where we're looking, how you're using TESS to kind of identify what this asker is categorizing as potential hotspots of life, and what type of life are we expecting to see?
Yeah, thanks for the question. Yeah, TESS is pretty remarkable in that its breadth of places that we can search allows us to look at essentially 80% of the stars in the sky that are bright enough for TESS to see, and that's millions and millions of stars. So in terms of where to look for a hotspot, we certainly are focused on the most nearby stars, because often those are the brightest. We often focus on both. For one argument is that we should look for stars that are very similar to the sun. So we look for sun-like stars, and we say, okay, well, there's life on Earth and planets like Earth around the sun, and so we should look for those kinds of stars. But of course, as was mentioned earlier, we know that exoplanets exist around nearly all stars, and so there's a lot of focus within TESS on cooler stars, stars that are sort of 10% the mass of the sun. They're much fainter inherently. And there's a lot of interest there because some astronomers think it's easier to find or to measure atmospheres of the planets around those. So from a SETI perspective, we also want to focus on those because there'll be complementary observations that are done. And to try to answer the final question of what we're looking for is it's very difficult to know, because just as all the SETI searches, it's difficult to know without more examples of the thing. But in general, we're looking for things that we can't explain by typical astrophysics, and we have had students in the past do projects that involve things like modeling odd shapes of eclipsing objects that could be passing in front of their stars that may be indicative of something that's not just a round planet going around a round star, which has a very distinct shape in a light curve, such as the TESS light curves. We've been modeling things that have very odd shapes, very artificial shapes, beyond just the things that we expect to see through the typical planet searches.
Thanks, Howard. Okay, so I'm going to bundle a few questions together in the interest of time because we only have a few minutes left. This ensemble of questions is for Dr. Lee because you mentioned commensal searches. So this question is, are antennas and the tools you use for SETI also useful for other functions in the space sector? And maybe taking some questions together, could you talk a little bit about the expected data analysis process, and in particular, why this huge single dish radio telescope?
Right. Yeah, so the commensal mode is easily understood since we are basically sensing the electromagnetic wave and just processing it with multiple set of we call backends, digital backend, basically industrial computers, to process them to suit each different scientific objectives. It can also obtain or analyze the signal transmitted by satellite. However, this antenna is not built for that purpose. So, for example, we cannot, since it's a very light and very large structure, so we cannot really track a fast-moving object across the sky. So most of the time, we are just listening, and but we cannot do fast tracking. The scientific data rate is about 6 gigabytes per second. So that amounts to about 20 petabytes per year. And that is a big challenge. I mean, the storage and just the simply the consumption of both the computer time and human time are becoming quite expensive. So we are still trying to improve and optimize the way that we are dealing with it. But for the sort of day-to-day scientific analysis, I think we are managing it. And on the SETI aspect, there is a dedicated SETI backend that has been developed in collaboration with the Breakthrough Listen team, and it has been start to function. But I think we need to invest more resource and make it function more efficiently. So I hope I answer some of the questions.
Yes, thank you so much. If the panelists are willing to stick around for maybe 2 more minutes, I'm just going to bundle another series of questions. This is the last one, and I apologize to everyone who's asking these fascinating questions that we didn't get to yours. So Steve, let's end with you. So something that I have talked with you a lot about, and maybe you can kind of answer this as Andrew did, both philosophically and technically. What limits do we currently have on technosignatures? So I'm just going to ask a few. Does your SETI search involve receiving artificial signals from other universes? And let me see one more. How do you explain, or could you just kind of meditate on extraordinary claims require extraordinary evidence? And I've put these 3 questions together just kind of based on our conversations. How do you kind of parameterize intelligence? How do the instruments kind of inform what kind of technosignatures we could receive? And how does that kind of process inform your imagination of who a technology using species could be, and where that signal could come from. So kind of, I guess the general question is thinking about the audience questions in tandem. How do you kind of relate your imagination of others with kind of the instruments that you have available in terms of, and how is that mediated by what a technosignature is or could be?
So we've got about another 20, 30 minutes for this, Claire. So let's see, I'll start with other universes. I mean, I think, there's often sort of people that listen to talks like this and sort of come up with ideas. Maybe they've sort of seen Star Trek and they're using subspace to communicate in Star Trek, or, they're sort of thinking, surely an alien civilization would be so advanced that they'll be using technologies that are beyond our imagination. And there's sort of a couple of things, I guess, that sort of we can respond to that with, and I like to quote Jill actually on this. One of the things that Jill has said is, we reserve the right to get smarter. So, we're doing the experiments that we know how to do right now. I wouldn't know where to start in terms of looking for signals from other universes. I don't even know whether that's sort of something that's possible within the bounds of physics. So we do the kinds of searches that we know how to do right now using radio telescopes. And actually radio, and optical communication are probably pretty good ways of communicating over large distances. And they're not necessarily something that's going to go out of fashion any more than sort of, talking to people has gone out of fashion since we've had the internet. Here we are talking, but we're sort of using kind of new modalities to do so. And I think, the other thing is technology may betray its presence in sort of interesting ways. And we have to go out and sort of do a search that's really sort of the broadest kind of search that we know how to do, using the instruments that we have, using the technologies that we have available. And once we've done that, then if we don't turn anything up, then we can think about how we need to refine that in the future. I guess to the first part of the question, sort of how much searching has been done. Again, sort of Jill has this analogy of a glass of water out of the Earth's oceans, and you hold it up and you see no fish in the glass, and you conclude, probably erroneously, there are no fish in the ocean. From this, we've now done probably more like a bathtub's worth of searching. And I think, something for me as well is that there may be no whales in the glass, there may be no, salmon in the glass, but maybe there are sort of microorganisms in the glass or in the bathtub that we could look for if we sort of, again, refine the kinds of searches that we're doing, even on the same data. And an interesting example of sort of extending the search that was done recently was Breakthrough Listen published a paper that was looking at about 1,300 nearby stars. And then in some work that actually just basically used catalogues of stars that were sort of in the background. This was some work led by some colleagues at the University of Manchester. They were able to expand this to a couple of 100,000 stars that were just sort of in the telescope's beam, but more distant, and thereby put more stringent limits on the number of stars that were sort of actively transmitting signals at the time of the observations. Obviously, we haven't made a detection yet, so we are sort of really still in the game of putting upper limits on this, but I think this is sort of a valid thing that you can do in science. It's a valid scientific question to ask. Similarly to, I imagine, sort of an expedition in the Himalayas looking for, rare snow leopards. And you don't just sort of peer around at the tent. I haven't seen any snow leopards, let's pack up and go home. You have to really do a comprehensive search. And the more that you look and the more different ways that you look, then the more stringent limits you can put on the population that's out there. And that's really what we're about right now. We hope that we spot a snow leopard someday. And again, we're sort of getting smarter at these searches. We're searching more of the haystack. We're getting sensitive to more and more different kinds of needles as we go. We don't know when we're going to have success at this. I can't sort of put a number on what are your chances of success, but I can say our chances of success are higher than they were 6 years ago before Breakthrough Listen started up.
Thanks, Steve. Okay, so let's wrap it up. So on behalf of the audience, I would like to applaud all of our wonderful panelists. Thank you so much. It's a really, really exciting time SETI and techno signature research. So thank you so much for being here and for talking about both the tools and the instruments that we use to do these SETI searches, but also kind of the profound and philosophical implications of what it would mean to make a detection. So thank you so much. So does someone from the IAF or Pascal, do you want to, I'll give you the last word. Oh, Pascal, you're muted.
Sorry. Yeah, I think it's wonderful, and you know, especially in these times, to dream and to talk about a subject which I think addresses all of us, and look at the technical details and how difficult it is, and what the future will bring. And I think a lot of people know about those subjects, but they don't know really the details. And I think it was great also for me to listen. And I thank you all very, very much of sharing this quite complicated topic with us. And we are very happy that you joined the GNF series, and thank you very much for coming, and I hope we see you in one of the next meetings of the IAF.
Yes, thank you to the IAF. Thank you, Pascal, and signing off.